Hi everyone again, and welcome to the second module on our battery management systems course. Here we will be talking about the sensing requirements and the sensing technologies, as well as the power connections in our battery management system. This is a quick look on the agenda. We will start with exploring the battery management system sensors, including how they monitor parameters like the voltage, current, and temperatures. And also we will review the different technologies that are currently used in this type of systems. Then we will explore the high voltage connections within the BMS, discussing how they manage power flow and how they protect against electrical risk. And finally, we will deep dive into the battery protections. So let's begin with the BMS sensors. In the BMS, to make informed decisions and to maintain the battery in a safety, in an expected performance state, we need to monitor several critical parameters. We need to monitor the voltage, and this is going to be crucial for knowing that the performance of each individual cells and the entire pack is the optimal. We also need to monitor the current, and the current sensing will ensure that the battery operates within its limits, and also it allows us to track the charge and discharge current rates. The temperature monitoring is very important because the batteries are highly sensitive to temperature, and a high temperature, for example, can accelerate the degradation and lead to a thermal runaway, while low temperatures can also be dangerous and be the cause, for instance, of internal short circuits. So the proper temperature monitoring will help us to manage all of these risks. And some other sensors that we may have are also, for instance, the gas sensing, that is essential for detecting any hazardous gases, and the insulation, that is relevant for identification of electrical faults that could cause, for instance, current flowing through the chassis of the battery and posing some safety hazards. So let's start with the voltage sensing. That is one of the most fundamental functions of the battery management system. The sensing of the voltage has different purpose in the BMS. We use the voltage measurements to monitor the performance of each of the cells, and for instance to detect if one of the cells is faulty, and also to detect when any of these cells is, for instance, in balance. It also helps us to identify over voltage or under voltage conditions, which could lead to safety hazards like the thermal runaway or faster cell degradations. At the pack level, this allows us to monitor and to optimize the performance of the battery, identifying, for instance, abnormalities and taking corrective actions based on those measurements. And the voltage sensing is also essential for estimating the state of charge and the state of health of the battery. All of this is achieved using different methods, but usually specialized integrated circuit or chipsets are commonly used for doing that. So the specialized chipsets, such as the ones from Texas Instruments, Analog Devices, or Onsemi, NXP, MPS, are commonly used to measure voltage accurately. They include sensors for every cell. This is a diagram. As you can see, every cell has an input for monitoring each of these cells, and to have a full monitor of the battery pack. And they are designed to operate in very harsh environments, such as, for instance, environments with high electromagnetic interference, heat, vibration, and they make them ideal for instance, automotive and industrial applications. Many of the integrated circuits that offer the cell monitoring also include built-in balancing options, either passive or active balancing. We will, in the next module, explore in detail what does it mean. But they are a complete package and they have a complete solution for managing the cells. Also, redundancy and fault tolerance are also supported by these devices, allowing multiple circuits to work together in parallel, for instance, to increase the reliability of the circuit. In general, the integrated circuits are going to be graded based on the safety level. So when we are having automotive safety automotive applications, in that case we will use the ASIL, that is a standard that is commonly used in the automotive industry. The chipsets then are designed for those automotive standards, and often they will adhere, for instance, in automotive to an ASIL C or ASIL D, ensuring like the highest level of safety and reliability. What does it mean to have an ASIL C or ASIL D integrated circuit? Basically, this implies that the chip integrates multiple measurement channels and adds redundancy also to ensure that even if one of those channels fails, the BMS will continue to receive accurate data and maintain a safe operation. Also, some of these chips include, for instance, self-checks to detect sensor failures or communication faults, and to immediately insulate the faulty components and prevent propagation of the errors of the systems, or to inform in case of any of those errors. When we are selecting the voltage measurement integrated circuit, we take into consideration different aspects. Some of the most important are, for instance, the number of cells that the integrated circuit can monitor and how they can be structured based on the battery that we want to control. We also need to take care of the measurement accuracy. High precision in the voltage measurements is going to be essential, for instance, to have accurate state of charge and state of health calculations. Many of these devices also include thermal monitoring, and it is interesting to see how they relate and if they are included or not. For instance, as you can see here, there is external temperature input in this integrated circuit. And finally, the redundancy and the safety compliance is another factor that we consider. ASIL compliance ensures that the chip will operate will have a safe operation even under fault conditions. And now let's focus on another very important aspect of the battery management system, that is the current sensing. The current sensor at the end allows the BMS to track the energy that is flowing in and out of our battery pack. By measuring the charge and the discharge rate, the system can ensure that the energy flow efficiently and within the safe limits. This data is also used for accurately calculating the state of health and the state of charge of our battery. The current sensor is also very important because it is the protective mechanism. It detects, for instance, overcurrent events, and also that are common in the case of faulty components that are connected to our battery, or when we have unexpected loads. Even they can detect short circuits, and in all of those scenarios, the BMS can respond quickly, activating protective circuits, disconnecting the battery, and preventing damage and failure in the whole system. We have many sensors that can be used. Here we will define or we will explain 3 of the most common current sensors. In general, the current sensing relies then on these 3 technologies, and each technology is tailored for very specific applications. First of all, we have the shunt resistance, and these are widely used because they are very simple and they are cost effective. In this case, we basically measure the current by detecting the voltage drop in this resistance. Next, we have the Hall effect sensor. This is a non-contact measurement, since they were detecting the magnetic field, and it does not require to have direct contact with the conductors of our circuit. And also we have the flux gate sensor that also detects the magnetic fields by means of the analysis of the non-linear magnetic properties that the core that we use has. In the upcoming slides, we will explore each of these sensors and we will have a greater explanation of their advantages, disadvantages, and use cases. So let's move to that explanation. And let's start with the shunt resistance. Maybe you have heard of this before, but these are widely used and not only in automotive, but basically this is the most commonly used current sensing technology that we can see available. The shunt resistance are highly valuable because they are simple, but they have also high accuracy and high precision in the measurements. And they are integrated. Usually we integrate these sensors in the circuit between the battery and the load. So here there is a schematic of the sensor. And if we analyze, if we want to measure the current that is going through our battery, we should connect the battery in one side of the shunt resistance and the load in the other side of the shunt resistance. In that way, all of the current will pass through the measuring element. A shunt resistance at the end will measure the current by detecting the voltage drop across its terminals, and this happens according to the Ohm's law. That is stated over here. As you can see, based on this, the voltage that we are going to be measuring is going to be directly proportional to the current that flows through the circuit and the value of the resistance that we are placing there. To ensure that we are measuring accurately the current, usually we use a 4-wire measurement technique. In this case, in this measuring technique, as you can see, we separate the power connection from the measurement connectors. It means that all of the current and the power will flow through this external loop, while in the internal loop we are having only the measurement connection, and this eliminates errors and it eliminates noise as well. Besides of that, another important consideration that we have to make when using the shunt resistance is the power dissipations and how there is a trade-off between that power dissipation and the measurement range of our system. So in this formula we can see that the power dissipated in this element is going to be or can be calculated as the current squared multiplied by the resistance. This means that at very high current levels, even with the small resistance values, we can have significant heat generation, and this will be leading to efficient losses in our system, and also it might even lead to having to require thermal management for that. So to accurately measure both at low and at high currents, the shunt resistance must be take a balance between the power and the range of it. Here at low resistance, we will reduce the power dissipation, but we will sacrifice the precision in detecting small currents. And when we have high resistance, we will improve the measurement accuracy at low currents, for instance, but we will increase the power losses at high currents. So there is a trade-off that usually the designer has to play with every time. Let's summarize then some of the advantages and disadvantages of this resistance. So in the advantages, for instance, we have that the shunts can measure a wide range of current amplitudes from few milliamps to over 1000 amperes. And another very important advantage is that they have a very low offset in the measurements. And also the measurements are linear over the entire voltage range. That makes them very easy to process that information. When they are made with high quality materials, like for instance manganese or nickel chromium alloys, in those cases the shunt maintain a precise characteristic and impedance across a wide range, but also is going to be independent of the temperatures. That is very important. And that's the reason why it has such a good accuracy and such a good resolution. However, there is nothing perfect, and there are also some disadvantages with this. While the shunt resistance are very excellent in the precision and in the accuracy, they are not so good in the power losses as we describe it. So at high current, we will lead to significant power losses and make the thermal management critical in those systems. Also, the efficiency of the system is reduced. They also have that the price is it varies a lot with the application where we are using. The specialized materials that are used in the shunt resistance will make the price either high for high currents or lower for low currents, so it has a very variable price depending on the application. But on top of that, when isolation is required, the additional circuitry will increment the price and because of the implementation that is needed. Despite of all of these challenges, the shunt resistance remain as the preferred solution for car manufacturers because they have a very good combination between the functionality, the accuracy, and the simple integration. So they are still very used. Here there are some examples, 3 examples of these, some of those resistors that we can find in the market. As you can see, they operate with measuring range that can go even up to 2,500 amperes. That is very high. And typically we can find shunt resistance below 1,000 amps as well. And here we also state some of the applications that they have. Some of them, for instance, this one is used in electric vehicles, also battery applications and battery energy storage systems, as in this case. The next sensor that we will analyze is then the Hall effect sensor. This is widely used technology for current measurements in the industrial and in the automotive applications because this sensor is reducing its price. Some decades ago it was very expensive. However, the advancements that in the design and in the manufacturing have made them more popular in the modern battery management systems, for instance. How do they work? And let's dive into the working principles of this. So when we have conductor, and when that conductor has a current that is flowing through it, it will generate a magnetic field, as you can see over here. The Hall sensor is placed very close to that magnetic field, and it will detect then the changes in that magnetic field. The magnetic flux will pass through the Hall effect element inside of the sensor, and here there are some Lorentz forces that will be acting and moving charges. At the end, this will create Hall voltage that you can see over here, which is going to be proportional to the current that is flowing through the conductor and also to the magnetic field that is being generated. This is the formula of the voltage that we are going to be sensing, and as you can see, there is going to be is equal to a proportional constant. This will depend on the materials that we are using. Also, it will be proportional to the current that we want to measure and to the magnetic field itself. The sensor will use as well some integrated circuit to amplify and to process this voltage, and to at the end to produce a usable signal, which may be an analog output or a digital output, depending on how we want to use it. This method is very popular because it is a non-contact measurements. It means that there is no direct contact with the conductor, with the conductors that are transporting the current. So that provides several advantages as well. Some of those advantages are that, for instance, unlike the shunt resistance, as we don't have the direct contact with the conductors, they make them resilient to very high current voltage, very high currents, and also very high voltages and voltage spikes that will improve in general the reliability and the safety of the sensor. They also have a very flexible placement. The Hall effects can be positioned anywhere alongside the cable that is carrying the current, and that offers a lot of design flexibility. This is particularly useful in vehicles where we may have diverse configurations of the battery or diverse configurations in the motor as well. And the sensors are also, as I mentioned, decreasing their price, so they are becoming less expensive, and they are very good in applications that already require the insulated output, and start being having competitive prices in those applications. On the other side, some of the disadvantages is, and one of the most important, is the offset, and is that the circuit and the sensor itself has electrical and magnetic offsets that are highly dependable on the temperature, and that at the end means that the measurement accuracy is affected. That is one of the biggest problems that it has. Nevertheless, many automotive manufacturers, especially in very cost-sensitive segments that require the insulation, use the Hall effect sensors and use it for battery current measurements as well. Here there are also 3 examples of those. As you can see how they visually look, you can see here the magnetic core, and here in this hole is where we place the conductor that is carrying the current. And regarding the ranges, we have also a wide range of currents. They can go up to 3000 amperes in this specific component. And the applications, they also have several applications. Some of them include the electric vehicles, and some other applications, for instance, switching converters, power supplies, welding machines, current protections, and so on. And the last of our sensors is the flux gate. This is a sensor that measures the current by detecting the magnetic field that is generated around the primary cable, very similar to the Hall effect sensors. However, these sensors in particular detect the variations of the magnetization in this core. It's a little bit more complex of the Hall effect, so I will try to explain the working principle as simple as possible. When we have a current that is flowing through a conductor, this current will generate a magnetic flux around it. The sensor will use that magnetic flux and will detect that magnetic flux by means of a core that also has a winding in the probe. The flux gate probe basically has an alternating current in that winding, and it uses to analyze the magnetization curve of the core that we are using. So to make it more clear, when there is no external current flowing through our circuit, in that case, there is not going to be any magnetic field induced in our core, and in such a way, the magnetization curve that we will be analyzing is going to be completely symmetrical. However, when we have a current flowing through it, it will induce an external magnetic field, and that induced field will cause an asymmetry in the curve that we will be trying to detect. The sensor measures the voltage that will be required to achieve the balance and to restore the symmetrical magnetization in the core. And that voltage is going to be directly proportional to the current that is going to be flowing through our conductor. That is a summary of the working principle of the flux gate. In general, one of the biggest advantages that this sensor has is that it has a very low offset, and the precision in the current is very high, especially compared to the Hall effect sensors. And even they are better in some cases than the shunt resistance in terms of the accuracy. However, the disadvantage is that they have a very high price, and even if they are becoming more affordable than before, they still carry a very high initial cost compared to the Hall effect sensors, and their advanced design adds some complexity to the integration in the systems that is required during the implementation of them. Another advantage that I forgot to mention is that similar to the Hall effect sensors, the flux gate sensors provide insulation in the measurements, and that means that we don't need to have a direct contact with the conductor, and also they are very flexible in where we place this sensor alongside the cable. That makes them also very interesting, especially in the electric vehicles. Here we have two examples of the flux gate sensors, one that is having a current range of up to 300 amps, and the other one that goes up to 1500 amps for applications, for instance, specific in the battery management systems and in the high voltage battery systems. To summarize, here is then a comparison of the three sensors that we examined before. In general, the Hall effect sensors are very cost effective, and they are very versatile, and they are excellent in applications that require a moderate accuracy and that they need, and that they have requirements for the insulation, for example in high voltage systems. On the other side, we have the shunt resistance, that they have an unmatched precision, but comes with the limitation of having the power dissipation, the limitations in the placements, and in the case of having requirements for insulation, then we have to include external circuits to isolate the measurement from the power paths. And finally, we have the flux gate sensors that offer the best balance between the accuracy, the isolation, and the flexibility, making them a very strong contender for the modern automotive industry, but so far they have limitations because of their high cost. And let's shift our focus now to another critical aspect of the battery management systems monitoring, that is the temperature sensing. The temperature in the battery has a very direct impact on the battery safety and the lifespan of the battery. Monitoring the temperature and managing the temperature is critical because the different variations in the cell temperatures can lead to imbalances, and they will reduce the battery pack efficiency in general. If we analyze the effects of the high temperature and the low temperature, we can find that when we have excessive heat, we can degrade the electrodes, we can degrade the separators and the electrolyte in our cell, and all of this accelerates the capacity loss and increases the likelihood of having thermal runaway and having any hazard issues with our batteries. On the other side, very low temperatures also are a problem, because at low temperatures the chemical reactions inside of the battery slows down, and this reduces the battery power output on one side, and on the other side, when we are charging at very low temperatures, this can lead to permanent damage in our cells and to increase the safety risk on the cells. Because of all of that, accurate temperature data enables the BMS to activate the cooling or the heating systems to maintain the battery within optimal temperature range. And the temperature measurement is crucial for any battery management system. Commonly, we use thermistors, and these are very used because they are compact in size, they have fast response times, and they are also very cost efficient, so it is the preferred solution there. Let's see how the thermistor works. And basically the thermistor is a resistor that is made of materials that those materials change the resistance in function of the temperature. Typically a resistor is going to be part of voltage divider circuit, as we can see here, and this voltage divider circuit is connected in series with a constant voltage source that may come from microcontroller unit. In this case, the voltage drop across the thermistor will depend on the thermistor resistance, and so on can be related to the temperature that it is being measured, and the way we relate it is with this formula over here. The measured voltage, then it is processed by analog to digital converters, or we can keep it as an analog measurement to then be processed by the battery management system. As you know, and as we can see over here, the resistance of the thermistor changes in a nonlinear way with the temperature, and because of that usually requires advanced calibration, or even in the processing of that information we need to have lookup tables to accurately relate the change of the temperature with a change in the resistance value. So it is one of the limitations that this sensor has. In general, we have two types of thermistor. We have the NTC, or the negative temperature coefficient. These type of thermistors basically have a resistance that will decrease as the temperature increases, and the contrary will be the PTC, that is a positive temperature coefficient. In that case, the resistance increases as the temperature rises. Between the advantages and disadvantages, some of the advantages of these type of sensors is that they can detect very small temperature changes, and they are very good in the precision. Also, because of the construction of it, they have a small size, and this makes them very easy to integrate in compact systems, and they are also affordable, so we can integrate many of these sensors in our battery packs, especially in large scale applications. And also the thermistors are characterized because they react very quickly to the changes and the fluctuations of the temperature, and that ensures that the BMS can respond in real time or respond fast enough. Between the disadvantages of that is, for instance, that the thermistors are very delicate physically compared to other type of sensors. Also, the precision of the measurement may decrease at very high temperatures or very low temperatures, and their accuracy in some cases is also affected by self-heating if it is not properly managed. But in general is the most common type of temperature sensor that are used in the battery systems. In addition to the voltage, current, and temperature sensing, the system and the battery management system monitors as well other critical parameters. Here we have some of those, for instance, gas detection and insulation detection, and we will briefly explain what are these type of sensing systems that we have to include in our BMS. First, we have the insulation monitoring, and in the insulation sensing, we are finally protecting against leakage currents and trying to reduce the risk of having electric shocks. For measuring the insulation of our system, we have two main methods. One is the resistance measurement, that is directly to measure the insulation resistance by applying a small voltage and monitor the current that will be flowing through that loop. And then we also have the capacitive methods, that in these cases we are measuring the changes in the capacitance and how that is related to the, for instance, the degradation of the insulation. This is particularly critical in high voltage systems that need to have this type of measurements to ensure compliance with safety standards and also to protect the final users of those vehicles. On top of that, we have the gas detection, and the gas detection here we are basically trying to detect any gases that can harm the users, such as for instance hydrogen, and those gases are released during overcharging or in case of thermal events. Some of the common sensors that are used here are, for instance, electrochemical sensors, infrared sensors, or catalytic sensors. Finally, we have also leakage monitoring. So leakage sensing is very important for detecting electrolyte leaks, for instance, that could lead to short circuits, to corrosion in our systems, and at the end failures in the battery. And in that case, the method that we commonly use to detect the presence of any liquid is the conductive sensing that you can see over here.